So we've spent our time creating approximations of area under the curve using rectangles by a couple of different methods. And one thing we've learned is that it appears that as we increase the number of rectangles and then proportionately decrease the width of those rectangles, that we get more accurate answers. The difficulty is, of course, that as illustrated in this small table, as we increase the number of rectangles and decrease the width, we have a lot of calculating to do. No one would really want to hand sum up 40 calculations of rectangles, which would be the case if we had a width of 0.1. And much less would we want to deal with a situation where perhaps we had a width of 0.01 for a rectangle, because then we'd have 400 rectangles to work with. Fortunately, there is a way to build a sort of machine on the TI 8384 that allows us to calculate all these rectangles and sum up the result. So to handle that situation, we're going to introduce two functions from the TI calculator. The first is sequence and the second is sum. Sequence you can find a couple of ways, but I choose to use list and then go over one to ops, and then notice the fifth item on the list, sequence. Okay, sequence takes a number of inputs, and we're going to review this, so just follow along. Don't worry too much about catching all the details. First, you input the expression that you're interested in. Then you indicate what within that expression is the variable that you're going to keep changing. You're going to make the initial position of the variable 1, in this case. You're going to make its final position 4, and you're going to move over by a step size of 1. So it'll go 1 to 2, 2 to 3, 3 to 4, and then stop. Let's just put this into the calculator. And again, if you have a different model of the TI, it will appear slightly differently, but I think you'll find the sequencing of inputs pretty self-explanatory. All right, we're going to enter this in and see what we get as a result. 1, 4, 9, and 16. So what has happened? Well, I hope you can guess that what happens is for each value of the variable, starting at 1, going up by 1, and stopping at 4, it displays what x squared is equal to. In this case, 1, 4, 9, and 16. Now that should be reminiscent of what we just worked on in the previous video. Namely, these are the same numbers that we found for the areas of the 4 rectangles when we were working with a right Riemann sum. We can change this to find the values of the left Riemann sum, for example, though. So, for example, just going to re-enter this and then work through the values. I still want to be working with the function x squared, so I'm not going to change anything there. I still want to work with the variable x, so nothing there is going to change. But to do the left Riemann sum, for example, I'm going to simply enter 0 to 3. And I'll still make the step size 1. So what do I get out of that? 0, 1, 4, 9. And if you'll recall, those were the areas of the 4 rectangles when we used the left Riemann sum. So this sequence function is pretty handy. In fact, there's something even better that we can add to it, and that is a sum function, which will add up all the results of our sequence. Now that's useful, of course, because our real goal was to find the signed area under the curve, not just the areas of each individual rectangle, but the areas of all the rectangles added up. We can also find the sum function inside list. So I'm going to go there. And now this time I'm going to go over to math. Notice the fifth math choice is sum. So I'll select that. And then I'll go back to sequence. Again, in list. And this time ops 5. Remember the sum was math 5. Go down, enter that in. And now I have the sum of the sequence of. This will take the numbers that I got from running this sequence, namely 1, 4, 9, and 16, and it will simply add them up. 30. I could do the same thing for the sequence from 0 to 3 with a step size of 1, and I would get the prior result that we had, namely 14, which was the left Riemann sum. But I hope what you're seeing here is the ability to make the calculator do most of the work by using this combination of sum and sequence. Let's recap what's going on. First, let's look at the sequence function. This can be found on your keyboard either in the catalog or with list ops5. And there are several inputs to this function. It's a fairly complicated one. First, the function that we want to sample at varying values. Then what will be the variable? This is almost always going to be x, whereas the function, of course, is anything that you're interested in sampling, and in this case, finding the signed area of. Here we have the start value and the stop value, and how to move from the start to the stop value, namely in what size increments. And so this function runs by saying, okay, the variable is initially set to x equals 1, and then it puts out what 1 squared is. It increases the step size by 1, so now the variable is 2. And it puts out what 2 squared is. It increases the step size again by 1, so now x is 3. It puts out 3 squared, and finally it reaches 4 and sets x equal to 4, puts out the square of that, and then stops because that's the value that you stopped at. The sum function, of course, is much easier. It just takes one input. In this case, the entire sequence function is what we're putting inside of it. And the sum up function, which is list math 5, adds up all of the values. So you can start to see why this would be a really useful way to construct an area finding machine. And with just a couple of modifications, we can turn it into a real general purpose area finding machine. But before we go on, I would urge you to take some time with your calculator and familiarize yourself either by reproducing the work that I've done or trying your own variation of it to test out the use of the sum and sequence functions. What I hope you've learned to this point is to understand the sum and sequence functions on your TI calculator. And as I mentioned previously, we're now going to get a little more sophisticated and build a truly general purpose area finding machine. The first change we're going to make is we're going to assign to y1 and y2 the particular function whose signed area we're looking for and the width that we want to choose for our rectangles. So work under the assumption that you've put in, for example, for the parabola x squared into y1, and let's say a rectangle width of 0.5. So let's think about what has changed in this description. First, our step size is no longer 1, but in fact, whatever the rectangle width is. Second, our area is not just the function, but the function times the width. Now you'll notice up here we didn't have times anything, but that was simply because the width in our initial cases was 1. More generally, we're always multiplying the height times the width to get the area of a given rectangle. And lastly, I hope you can think this one through, but notice that whereas before we had to explicitly say start on the right side of the first rectangle and end on the right side of the last rectangle, or when we changed this to 0 and 3, we were saying start on the left side, end on the left side of the last rectangle. depending on whether we were doing a right Riemann or a left Riemann sum. Now, in this case, we're doing a left Riemann sum, but we're always stopping one rectangle short of our end goal. So we want to find the signed area from 0 to 4, but the place where we're going to find the height of the last rectangle is going to be at 3.5, just because the width we were making 0.5. Okay. With this generalized format, we now can input any function we choose, and to any precision that we want, set the rectangle width smaller and smaller and smaller. So let's just do that. I've got here, I've set up the sum and sequence with the revision, namely y1 times y2, 4 minus y2, and y2 for the step size. And if you're curious, you'll see that I set y1 equal to x squared and a step size to 0.5. So coming back to the function that we had, okay, if I enter this, we now get 17.5, which, if you go back and check the other video, was exactly the value that we got for left Riemann sum with a width of a half. But the beauty of this is now that we can deal with the step size all in one shot, we can simply change the step size, for example, to 0.1. Put that in, and we'll run our calculation again. Okay, same formula, but it's the step size that I've changed. Let's see what we get. Now we get a value of 20.54, which, if you recall, was closer to the trapezoid approximation that we got for a width of 0.5. But we can go even farther. We can go all the way down to a step size of 0.01. Think about what we're doing here. We're actually causing the calculator to find the areas of 400 different rectangles and then adding up those 400 entries. It actually starts to take a few seconds for the processor to calculate, but we get 21.253. It appears that we are getting increasingly accurate as we use thinner and thinner rectangles to approximate the area under the curve. So let's see if we can't sum up what's happened as we've built this general signed area finding machine. We want to increase the number of rectangles. It improves the accuracy, we have reason to believe, but it's very tedious. But by using the sum and sequence functions, we can make the job reasonable. And in particular, if we add the additional sophistication of setting out the function and the rectangle width as y1 and y2, then we have a complete general slope finding machine that will accept an arbitrary function, an arbitrary rectangle width, and calculate the signed area from an arbitrary start point to an arbitrary end point. I encourage you to play around a little bit with this. I can't tell you exactly what you should try, but I hope you can enjoy working with the sum and sequence and perhaps teaching someone else how the whole thing works to really solidify in your mind what is going on with using Riemann sums to approximate the signed area under a curve.